focus on yet another topic that is going to be battery management system for automotive systems. Okay, so how to what are the things which we need to focus, those kind of things, okay, which we're going to focus on. So with that being said, let me just start the session. I'll just share my screen again, and shortly we will be seeing the screen.
Yeah, your
And
screen is perfectly visible and your audio is
yeah,
also
thank
perfect.
you. Yeah, thank you very much. So in that case, let's just pop into the session for today. So today we're going to see again. Today our objective is not to focus more only on theoretical aspects of the battery management system. Okay, but yet another tool. Okay, on how the NI based tools, because as I've already explained to you yesterday, okay, I am a Labview developer focused on several domains, okay, which Labview as a tool is being used in industries all around the world, and how this tool can be used to solve problems. But again, as I already told you, any tool can be used, but the important thing is you have to use the right tool for the right problem to be solved. Okay, and for simulation of BMS, there are several tools available. Okay, but we should not stop with this simulation alone. Okay, because what we have to plan is after simulation, what is to be done. Okay, and how can we proceed with it, right? So that is what makes the tool important, because one after your simulation job is done, you should not be like, okay, we have to use another tool for implementation part. So if you see LabView, since LabView is a tool used not only for measurement, okay, but also for control, totally for automating of all these things. Okay, LabView is used in industries for both simulation as well as implementation. Okay, so yesterday we already saw the simulation part, and due to the limitation of this, this offline online course, okay, we may not be able to have an actual hardware hands-on experience, but today we'll be seeing how LabVIEW will interact with a hardware. Okay, it's not a very large hardware, but all the type of hardware works the same way. Okay, so we'll have an exposure at least, okay, on how it's going to work, right? So that will be done for the day. But anyway, let's just see on why we need to go for battery management system. What is the reason? Okay, anyway, everyone knows about what exactly battery management system is. Okay, because research on battery management system has been going for a long time now, so it's not really a basic thing. Okay, but what are the things lab we can offer? Okay, for us to implement this battery management system, and how people have done it. Okay, using this NI based tools. Okay, is what we can say it's going to be the grand takeaway. So we all know that core composition of electrical vehicle. Okay, these are the primary components. Okay, if you take any electrical vehicle, we have the traction battery, which enables us to power the battery for to move forward, okay, or backward. Okay, basically to propel, right? So it's going to provide the most power. And next one is going to be the power converter or inverter. And third one is going to be the traction motor, which enables the conversion of electrical energy to the mechanical energy. And your NI based tools, okay, provide support in all these three form factors, okay, for all these three important aspects. Okay, but today we are going to focus on how battery is being supported and what are the things which we can do. But first, why? Because we need to know why, then we need to know what, then we need to know how, right? So automotive systems have been there for century. Okay, so for I don't know, for 100 years, okay, or more. And as electricity came inside, okay, people started using lead acid battery, um, because of the even though it was more heavier, okay, it was more stable. And we, in order to charge it, people just need to in order to make it a better, okay, not to make it hold more charge, people just need to add sulfuric acid inside it. and it was good to go. Okay, as long as the electrodes were perfect. But lead acid batteries were not able to hold that much power. Okay, compared to lithium-ion battery, and due to the advent of lithium-ion batteries, okay, people started seeing the advantage of it. Okay, it was able to more hold three times more its potential, three times the potential of same weight compared to the lithium-ion battery. I mean, lead-acid battery. Okay, specific energy. Okay, that's the key term here. Okay, specific energy. If you say 1 kilogram of lead-acid battery can hold 35 to 40 ampere hour. Okay, the same weight of lithium-ion can hold possibly 100 to 265 watt of the same weight of lead acid. Okay, basically its electro potential weight, okay, was higher. Okay, so which opened plethora of opportunities. Okay, plenty of opportunities. Okay, previously this lead acid based systems were able to power small electronics on board the electrical systems of a in the internal combustion engine. Okay, and to charge and discharge it, I mean discharge it. Okay, people used dynamos from an internal combustion engine. But you know when people started seeing the potential of electrical, the lithium-ion battery, people said, okay, fine, we can use the lead acid, lithium-ion battery. Okay, means we can power. It can hold more power, which means it can discharge more power. Okay, potentially power more heavy electrical systems. Okay, like an electrical motor, for instance. But there are again disadvantages due to this, and we all know that. Okay, so like lead acid battery, even if you overcharge it, okay, over voltage, if you, I mean, significantly higher voltage, even if you apply, okay, it's not going to damage it right away. Okay, so not much damage will be concurred. Okay, and even if you overcharge it, okay, over voltage applied, okay, it's going to apply the pass the current to next cell. Okay, and the cell equalization is natural over there. Okay, there is no need to add cell balancing methodology over there. But lithium ion battery, on the other hand, okay, lithium is a very volatile substance. Okay, it is prone to heat based damage or overcharging, undercharging. Okay, every problems, whatever problems were is sophisticated with respect to battery. Okay, it was focused, okay, on lithium ion battery because it's only for the reason that it's going to be very volatile material. Okay, so even over voltage in a single cell can cause extreme damage. So these were the challenges, okay, with lithium-ion battery. Okay, so charging needs to be taken care of. A specialized circuit or smart charging unit must be set up, okay, in order to prevent over voltage from being applied across the terminals of the battery. And of course, discharging as well. Okay, so you can discharge the lead acid battery safely, even to 0% of SOC, state of the charge, okay, with little light cycle damage. But your lithium ion battery, we set the state of the charge to 2 volts. Okay, so that is per cell. Okay, so individual lithium ion battery lithium ion cell can hold 3.7 volts. Okay, so it can be discharged up to 2.0 volts. Okay, nothing below that. Okay, so if you go below that, potentially it could have serious damage issues. Okay, the electrochemical balance inside it is going to be lost. Okay, and its total life duration is going to be lost. It cannot hold the previous power it was able to hold, right? So it's going to be gone forever. So discharging also needs to be taken care of. Okay, you should not allow it to discharge to its minimum potential. So in order to tackle all these things, okay, to tackle all these things, we all know possibly that we have an embedded system, or you can say electronic unit, okay, which is going to um, monitor and potentially control all these things. That is what we call it now as battery management system. And battery management system is, to put it simply, okay, it's a unit, okay, which is going to monitor and monitor the charging, discharging, and the temperature, focus of a battery, And if any of these parameters are out of range, it will, and potentially it will try to control it as well. Okay, depending on the sophistication of the BMS which we have selected. Okay, but mostly it's for monitoring and logging data. Okay, but if needed, it also enacts the control mechanism as well, right? So a battery management system is available starting from your mobile phones nowadays. AI based battery is available even in your mobile phones. Okay, compared and along with other systems like now automotive, that's what we are talking about. Other apart from that, we have BMS in spacecrafts, any component, any systems which have battery in it. Okay, like a large amount of battery in it, so it's going to be available there. So what are the basic block diagram of battery management system? What does it contain? What does it have? Okay, so these are the important aspects to understand. Okay, and if you look at it at a low level, okay, battery management system is going to contain a data acquisition system. It's going to have a hardware, okay, or an embedded unit, which is capable of measuring parameters like voltage, current, temperature. Okay, it's capable of measuring all these things. And once this is done, okay, so it should also be having a separate unit which is capable of determining the state of the battery, whether it's it's properly working, okay, it's in unknown state, or the known states like how much charge is present. Those kind of things should be you know monitored. The state of the charge, state of the health, okay, all these things should be monitored there. And once this is done, okay, these are going to be the algorithms. Okay, this is going to determine based on the data available, and then ultimately you're going to have a dashboard to view the status of the battery. Okay, like in our mobile phones, we have this charge indicator, how much charge is available. Okay, similarly for your automotive system also, we need to know how much distance it can go further. Okay, how much charge is available. Okay, those kind of parameters need to be observed. Okay, because um, the range anxiety in automotive units, that is your automotive systems, are is very prevalent. Okay, at least in electrical vehicle based units. Okay, in other units at least we can somehow um, you know refuel our your vehicle. Okay, but in your battery operated vehicle, that is fully electrical vehicle. Okay, unless we have a way to change the battery on the run, okay, it's not possible, right? So there should be a reliable user interface which can monitor all these things. And depending on the state determination, we may need to employ some sort of electrical control, maybe potential safety protection, okay, like enabling the relay, okay, or enabling the disconnection and connection of the load from the battery, okay, when necessary. Okay, that is going to be determined by state determination. Or it need not be electrical parameter based safety protection. Okay, maybe thermal management need also be done. Okay, when the battery gets too hot, either we need to switch off the load to the battery, or depending on the severity, if it's very severe, disconnect it. Okay, if it's not so severe, maybe we need to employ some coolant mechanism. Okay, cooling mechanism like circulating a coolant around the battery or wherever it's necessary. So these are the things, okay, which are important in a battery management system, which needs to be employed. But why? I mean, we already know why. Okay, but still, what are the reasons? And of course, why the reason for going for BMS is, okay, to monitor and balance each cell. Okay, so the thing here is, in an individual cell, electrochemistry is going to be different. Okay, one cell, no two cells can be like same. Okay, so it could have different balance of chemicals inside it. Okay, due to that, impedance could be different. So charging and discharging rates will be different for different cells inside the battery. So ultimately, appropriate cell balancing should be employed, okay, in order to prevent uniform, not to mitigate uniform charging, and according to the capability of the battery, okay, it should be employed. Or discharging also, okay, so just because the impedance of one cell in a battery is less, okay, it should not be like one single cell maximum current should be withdrawn. Okay, so appropriate cell balancing mechanism should be employed. Okay, by doing this, you are going to extend the battery life because it doesn't get damaged. Okay, even if a single cell is damaged due to excessive say usage of cycling, okay, it's going to damage the whole cell at the whole battery at the end. And by extending battery life, you're also going to extend the capacity, the full capacity, right? So instead of the battery losing its the life in, let's say, 1 month, okay, not half of its life in 1 month, let's say, for example. Okay, by employing all these things, okay, you're going to extend it. Let's say in 1 month you might have lost only around 5%, okay, something like that. So these will enable us to do all these things. And of course, so depending on the load, okay, your battery discharging, okay, at least for electrical vehicles, the amount of current which is going to be drawn is going to be in terms of hundreds of amps. Okay, so you're going to have a very large amount of heat dissipated, and due to that, we need to make sure that the heat is properly dissipated from the system, okay, so as to not make the lithium ion battery combustible. Okay, so these things could be employed. And of course, we all know about. Of course, you may be knowing better than me. I think I heard something. So okay, it's just, yeah, fine. So ultimately, these are the things which battery management system will be responsible for. You will be having a monitor unit which will be monitoring the parameters. Then based on the data parameter monitor, you're going to compute some certain other data. Okay, so once you have computed the other data, okay, maybe we need to communicate it to other systems inside the electrical vehicle, because when you take an electric vehicle, okay, it's going to have multiple components inside it. It's going to have something like uh, it's going to have it's going to have battery, okay, as a system. Okay, it's going to have an inverter component as a system. Okay, it's going to have a motor, more control and monitoring it as a system. Okay, it's going to have you know um, your let's say car door monitoring system, windows, okay, those kind of things will be available there. So every system needs to be connected to a centralized unit. So from that, we will be able to communicate with it, right? So, and again, HMI based system. Okay, so even in car also nowadays we have this human dashboard, okay, human machine interface, where we can command what are the things to be done. Okay, if you want to open Windows, okay, Windows or car, okay, you'll be having a centralized system. In that same HMI, you'll be monitoring the car available range or the battery life. Okay, how much life is there, whether you can say whether a maintenance is required. Okay, those kind of things can be seen over there. And protection. Okay, so like I said, okay, like due to the let's say dissimilarities, some sort of mishappens tend to happen. Okay, and in order to protect us from, okay, let's say the current consumed, okay, it's very higher than the normal value. Okay, so it's not anticipated. So maybe we need to disconnect the load from the the battery. So this type of production unit, okay, should be is the job of the battery management system. Okay, so production or battery connection to load circuit. Okay, this could be enabled or disabled, and also energy recovery. Okay, so from doing a break. Okay, so maybe energy recovery also, it's very specific to EV. So this could be employed by a battery management system. But what are the parameters which we need to monitor, tend to monitor? Okay, we have parameters like voltage, current, and temperature, which could be monitored directly. Okay, so these are the three components which will be typically monitored by the BMS. Okay, we'll be having a voltage measurement in it, current measurement in it, and temperature sensor. Okay, which will sense the temperature data of the sensor value of the battery. Then based on this values, okay, we'll be able to compute the secondary values like state of the charge and state of the health. Okay, state of the charge and state of the health cannot be directly measured. Okay, like measuring voltage current. Okay, because it's a derived unit. But these are the things which will be monitored by the BMS. And we all know what a state of charge or SOC. Okay, it's going to be, you know, the amount of the percentage of charge available compared with the total capacity of the battery. Alright, so if you say total capacity of the battery is like 1 kilo ampere hour, okay, so how much is available as of now? So that's going to be the state of the charge. And state of the charge, okay, so it depicts how much charge is available inside the battery, okay, and how much further it can go. There are plenty of ways to make the estimation of the state of the charge. Okay, we make use of either a direct measurement. Okay, even though we measure it directly, okay, we are going to make use of some formula. Okay, to convert this measured data to actual value of state of charge. Okay, we also tend to make some bookkeeping estimation. That is, we will map values from 100% of charge to a particular voltage, and 100 particular voltage will be mapped along with 0%. So anything in between will be accordingly mapped according to the percentage. Okay, so that will be done. Bookkeeping. Okay, so we'll follow a formula. Okay, which will interlink both voltage with SOC, and this may vary with respect to the you know the type of battery which we use. And nowadays, since the advent of machine learning, okay, people have started experimenting in adaptive systems, okay, where they use algorithms to train their model, understand what will be the parameters. Okay, when it is 100%, what will be the parameters with respect to 90%, 95%, or something like that until 0%. So your neural network or whatever algorithm which you use, okay, it should be capable of finding the relationship between input and output and create a model. Then basically use that model to estimate what is the current current um, percentage, okay, or state of charge. Okay, so there are plenty of ways to measure the SOC. And even in these categories, okay, we have several other methods, okay, which will be predominant in understanding and identifying what type of component is. And state of the health. Okay, that is for state of the charge. Okay, the problem with state of the charge is, even though theoretically you can say that the battery will always be having this. If you take 10 kiloampere hour battery, if you buy it, okay, so we can assume that it's going to be always staying as 10 kilo ampere hour. Okay, but unfortunately such is not the case. Okay, every product created, okay, is going to go through some sort of degradation, okay, due to wear and tear. And you might say that it's going to be 100 watt or 100 ampere hour battery. Okay, original capacity maybe during the production, okay, it was 100 ampere hour. Okay, but unfortunately due to wear and tear, it's going to reduce to, no, let's say 80 percentage of the 100 watt hour. Okay, which is going to be the new 100 percentage. Okay, new 100 percentage SOC, that is going to be 80 watt. Okay, it can only discharge up to 80 watts. Okay, because due to the changes in chemistry inside your lithium ion, due to conditional wear and tear, it keeps on degrading. Okay, up until the point, okay, we charge it and discharge it until it cannot hold much charge. So state of the health is basically the amount of charge it can hold compared to the original capacity. So, and this also is going to be, it's going to be like a curve. Okay, we're just going to compare the with respect to number of charging cycles with respect to the state of the health. Okay, you can see that every time when we take a look at batteries, capacity. Okay, they will say that it's going to hold this much amount of ampere hour, but terms and conditions will be until number of cycles, some number of cycles, let's say 500 or 1000 number of 1000 cycles of the cycles means charging and discharging cycles. Okay, they would have clearly mentioned in the data sheet. Okay, maybe not on in the battery itself, but this will be clearly mentioned in the data sheet. Okay, model. Okay, so it can hold only up till that, but after that its characteristics may change. Okay, may change, but most of the times it does change. That's the truth. Okay, so here they are saying, okay, up until 500 charging discharging, okay, it will be like 100%. Okay, every time it returns to the same voltage level. But you can see the trend as it exceeds the 500. Okay, you can see that it's going to be like, it's going to become 100,000. Okay, so it's going to become 60% at 1000 cycles of charging and discharging. Okay, what I mean here is, okay, it's going to be 100,000. Okay, it's going to, after charging it about 1000, 500 to 1000. Okay, it's going to slowly become little bit less efficient, and you can see that it's going to slowly regain its posture. Okay, so it's at 1500. Okay, it's going to become 40, and at 2000, okay, you can see it's going to become 30. Okay, exponentially it's going to slowly, it's going to reverse exponentially, it's going to, okay, and at the end of the time, okay, after at 3000 cycles, okay, it's going to hold, it will be able to hold only 20% of the original, the energy. And based on this voltage, current, and other every data we collected, okay, we'll compute certain other components, okay, which are better for diagnostic purpose. Like how much is the maximum charging and discharging current, okay, of the if of your battery. Okay, so since your BMS can typically measure the temperature, okay, I mean not temperature only, okay, it's going to measure voltage. Okay, it should be able to measure all the, compute all these components as well, values. Okay, like how much charge it can hold, or maximum discharge current it can get through, or something like that, right? Then energy they get since large charging cycle. Okay, since we're talking about electrical vehicles here, okay, so we need to know how much charge was expended for this much number of distance travel, like mileage. Okay, we need to know mileage. We need to check whether the mileage is reducing, which means the battery is wearing out. Okay, so those kind of information, okay, insights need to be, at least for the manufacturer perspective, this needs to be accounted for. And internal impedance of the cell, charge, delivered or stored. Okay, these components will be monitored by using a dashboard. either for personal use, mostly not for personal use, but mostly for diagnostic purpose of by the automotive manufacturer who's providing service. Okay, and you can employ these kinds of production system, okay, typically meant for batteries, okay, over voltage, over current, under voltage, under current, okay, under temperature, over temperature. Okay, so these are the important, very well known parameters, okay, for a battery. Okay, this will be monitored. And one exemption is lithium magnesium hydride batteries. Okay, they require over pressure monitoring. Okay, but most of the time we don't see anywhere people using this kind of battery for EV. Okay, mostly it's lithium ion. And production system. Okay, it could be a electromechanical relay. Most of the time, not. Okay, so we'll be either using an electromechanical relay or SSD. Okay, or in terms of temperature, okay, we will be seeing something which is capable of circulating the temperature, the heat. Okay, for to carry heat from the radiator to the radiator from the heating places. Okay, maybe battery or whatever it is. And yes, so these are the things which your BMS is capable of. But next to answer, what are the topologies the BMS has? So this is another example of how a BMS will look like. Okay, it will have a measurement unit. Okay, it's just going to measure voltage, current, and temperature. Okay, and we have three types of BMSs. Okay, so in terms of topology, okay, in terms of application also it will vary. And number one is going to be centralized BMS. Okay, where you're going to have an embedded system which is capable of measuring, okay, individual temperature of individual cells in the battery pack. Okay, and it is also capable of measuring the current through the whole system unit, so provided it's capable of measuring. It's going to have the sensor is going to capable of measuring the temperature, current, and next one is going to be temperature. Okay, these values are going to be measured. Okay, and this is going to be acting as one single unit which can measure all, let's say for example 80 cells in a battery pack. Okay, the advantage is you're going to use less electronics, but the disadvantage is going to look a lot of wire intensive. Okay, it's going to have a lot of wires in it. Okay, and all these wires is going to be connected to a single unit, which makes it a less attractive place to work with, and it's hoping it to not have any bug. Okay, bug in the sense, in this case, defect, right? So for a small unit, okay, this centralized BMS could be used. Okay, but when you're most of the time when your electrical vehicles will have a battery, okay, different multiple battery packs inside the battery, different battery packs will have single battery pack, and this single battery pack will have multiple batteries inside it. Okay, it's like it will keep on growing. And individual cells can be directly sometimes monitored. Okay, but if you can, okay, you need to go for you have one more option called a centralized BMS. I mean, distributed BMS. Okay, where individual each and every cell, okay, each and every cell there, okay, in your system, okay, it's going to recognize. Okay, it's going to be having this intelligent unit. Each and every cell, okay, is going to have this embedded unit. Okay, this makes it look less, you know, susceptible to wire connections. Okay, but the problem here is it's going to be very costly. Okay, because for 80 cells, you'll have 80 individual microprocessors, and each and every cell will have one. Okay, it's going to be very, very, very costly. Okay, but it's going to be more reliable, and it's going to, every each and every cell is going to have controller, and it's going to be connected by a protocol. Okay, and this protocol is potentially it will be a bus-based protocol, right? And it will be communicating to the master. Okay, entire master. Right. So again, this is going to be a very costly affair. Okay, and this could be potentially used in, let's say, in a train. Okay, a locomotive based train. Okay, where you have multiple battery packs in one single station, so it will be easy for us to monitor it. So we don't want more wires, and we don't want it to make it costly. So instead of going for these two options, we have third option that is going to be like a modular, okay, or you can say hybrid. Okay, where we have the same type of number of cells. Okay, but here the thing is we are trying to use less number of slave components, and also balancing, loading each of them with equal number of cells or something like that. Okay, at least equal number of cells. Right, so individual slaves will be allotted to monitor some sensors. Okay, so and these sensors, this slaves will be communicating to the main unit. Right, and the main unit will communicate with the communications environment or the main computer, and you can observe all these things. Okay, so this is what I mean. Everyone knows about the BMS. Okay, it's going to be basically a data access system. Okay, so what can help us to implement these things? Okay, it is not only simulation. Okay, simulation, yes, you can simulate the algorithms. Okay, on how to make the data system acquire the data and just implement it later. Okay, yes, that is surely it's possible. Okay, but what is the best way to not only create the algorithms but also to visualize the data from the algorithm to output, and after that we should also be able to see the implementation part and control the actual BMS, actual the implementation of a real world BMS. So how can we extend this roadmap? So to do this, there are plenty of tools available in the market. Okay, we all know that again, but an appropriate tool here is because engineers and scientists are better at understanding how a battery works instead of using a scientist create algorithms and expecting the um, your programmer to understand it and programming in the correct way in a short time on it. Okay, it's going to take a risky gamble. But instead, we all know how Labview is easy. Okay, how easy Labview is. So instead of just worrying about it, you can make use of this. Okay, Labview environment. Okay, and since engineers and scientists are very good at flowchart creation, okay, their program is basically flowchart. So it will be easy for them to implement. So that's why we'll be seeing on how we can implement this using Labview. But why do they use Labview here? Okay, number one, Labview is curated for engineers and scientists to create an application, and it interacts with several hardwares which are in line of data acquisition, which is the backbone of battery management system. Then also, not only is NI providing this Labview tool and the hardware. Okay, if you are not comfortable with NI hardwares, but you're good with Labview software because it's easy to visualize things. Okay, then we have the support of third-party tools with Labview. Okay, not only is NI tools programmable with Labview, you have third-party tools. Okay, like Bloomy here. Okay, they provide solutions using LabView plus their own hardwares. Okay, so it's not like people have to be dependent on any hardware for everything. If appropriate driver is available, it's going to be available. And to program that hardware of its own, list, you can make use of this and do it. Okay, so if you see the programming nature of your industrial DAC. Okay, industrial DAC in the sense the a typical DAC which is used in industry to make measurements of appropriate kind. Okay, it could be a semiconductor measurement, it could be automotive measurement, it could be automation based measurement, anything. So NI has an appropriate cards like that. Okay, not to make appropriate measurements. Okay, from low power, low speed USB based hardware to high channel, high throughput synchronized measurements from a computer instrumentation computer called PXI. Okay, there are plenty of objectives which are available. Okay, fine. So this is as I already told you, okay, we don't have an access to PXA obviously, okay, because most of the time it will be a very bulky object, okay, and it will be capable of, it will be too, it will have all the parameters as well, okay, but we don't have access to it. So instead, in order to gain the same experience of making measurements using LabView, okay, we have with us uh, a hardware called as NI MIDAC, okay, which is capable of making measurements of voltage, okay, directly, and by using appropriate sensor, we can also make measurements of current as well, and if required, temperature as well. Okay, these things can be measured seamlessly. So you might ask, how is it really possible? So because one misconception with LabView, every people think is LabView is a program, not a programming tool, it's a simulation tool. Okay, it's just used for simulation. That's what people think. Okay, but real-time implementation is the advantage of LabVIEW. So this is how the DAC looks like. IDAC, the one which I have with me, looks like. Okay, it's powered by USB, which means I don't need to give an extra power supply. It's powered totally by USB. Okay, only thing we need to do is in order to access it, we just need to connect it to your computer via USB provided. Okay, it's going to be done. Alright, so it's going to have its own specification. Okay, so let's see how we can set this data action hardware up. Then we'll see what are the things which we can do by using this data action hardware and how to make measurements using LabVIEW and so on and so forth. So right now I just connected my DAC hardware to my computer via USB. So by using one more application in NI's portfolio, okay, called as NI Max, we can see whether the hardware is actually connected or not. Okay, we can open this, the NI Max, and we will be having this left side drop down box, okay, where we can search if any hardware is connected properly or not. It looks like, oh, now the hardware is connected, right? So I can either configure it. Okay, for this particular card, configuration will not be that much. Okay, you can set like if we have additional template and additional components. Okay, not interact with it. If you need, you can use it. Okay, so if you want to test it, okay, you have a function called test function. Okay, if you want to quickly test the hardware, okay, that also can be done easily. So like here, if you see, we have two channels of oscilloscope. Okay, meaning we can make some measurements of analog input. Okay, I can select the hardware is there. Okay, I can select the A0. Okay, if I want it to be A0, okay, A1. Okay, similarly, we can select whatever things it's best. Okay. So to check it out, okay, I'm just going to AI0, AI0 is connected. Okay, I connected to on-demand right now. So okay, so I'll just run this. So by default, it's a type of chart which goes from left to right. Okay, now we have connected the hardware. Okay, we have also made the connections of analog output to analog input, meaning we can generate from analog output and generate an analog input. Okay, so you can see that. Okay, we just connected AA0 and AA1 together. Okay, now I'll go to AO0, sorry. Okay, we'll set the actual hardware. Okay, I can set the drop down list. Okay, and we can set AO0 only. And you don't need to do anything here. We just need to click on update. And you can see it's going to generate some value. Right? The problem is this is a place where you can configure the hardware or debug the hardware if it's working fine or not. Okay, but development is done fully using Labview. Okay, so yeah, let's see about this DAC hardware. Okay, so if you see, even if you want to create your own application, okay, you have certain toolkits inside in LabVIEW. Okay, in order to interact with hardwares. Okay, like if you see, we have NI's DACMX hardware which is capable of making measurements of analog input and output, analog digital input output. Okay, but sometimes we need to make specialized measurements. Okay, so there will be specialized hardware available with NI. Okay, called scope, FGen, DMM. Okay, DC power. Okay, so if you want to check whether your battery is charging properly or not, okay, we need to sync some voltage to it, sync some current to it. that current will be provided by your charger. Okay, so that's what is available over here. You can develop your own. You can say it's virtual instrument because programs in Labview are called virtual instruments. The way we create this program, we call it as uh, wiring. Okay, we call it as wiring. Okay, and right now it's not like entirely necessary for us to create a program to access the DAC hardware. Okay, as I already told you, since NI LabVIEW is a virtual instrument based platform, there are always some options available during this simulation of your. Now we need to use appropriate hardware to measure it. Okay, we need not use um, we need not create your own application. Okay, there are some existing applications which will make sure to emulate the appearance of the instruments. Like for example, if you see oscilloscope, I just need to type oscilloscope once the appropriate software has been installed, and it's going to be available. And we also have some more instruments. Like say if you want to do a function generator, that also will be potentially available. And the advantage here is I don't have anything, like I have very small box available with me here right now. Okay, but if you want to go for multi-function, multiple cards, something like that, then potentially you need to go for MyDAC or MyDio. Okay, so to give an example here, if you see we have this function generator. Okay, we have this NI one. Okay, we select it and we just run this program, and there is no indication of whether it is happening or not. But in real world, I have this DAC with me, and this DAC we have this analog input and output, digital input and output. So these are available. Okay, so we can make use of it. Okay, so we have to view the functional data. What I have merely done is I connected this functional data and oscilloscope together in real world wiring. So I just run this merely, and you can see that whatever data was generated in the functional data is available in the block diagram, and it's available in the oscilloscope. Apart from that, they are giving different values which might be seemingly important. Okay, so if I change the frequency, okay, this is also going to increase or decrease. Okay, so measurements can also be synchronized. Okay, let's say you want to make measurements from one single cycle, zero half, zero cycle or something like that. Okay, you have some type of trigger available. Okay, you can say it's triggering, and from here you can yeah. So I need to set the channel source. Okay, I didn't run it. Sorry. Yeah, if you compare it with the immediate, okay, immediate keeps on moving. There is no synchronization. Okay, but if you see edge, it's always going to start from this location because you're given level as 0. Okay, you're saying channel source. This from this source. Okay, this much, distance should be there. Okay, something like that. Right, but here this is a fixed oscilloscope and this is a fixed functionator. We cannot add anything to it as of now. Okay, that is anomalies. We cannot add anything. Maybe the NI if it comes with appropriate way to make these measurements. Okay, unless the programmer decides to create his own user interfaces. Okay, then they can go ahead. Okay, potentially using Labview to create their own instruments. So any questions, please let me know.
Sir, for this Labview, you have not connected any hardware. Now that DAQ, what is the exactly content of it, sir? Because generally emulator or you are using as a
No, 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 no,
emulator.
no emulator, ma'am. Actually, I'm using an actual hardware here. Maybe I can. Okay, I can switch on my camera and show that it's an actual hardware is there, but I don't have any DUT connected to it. Okay, if that's what you're expecting, I don't have an actual battery with me. Okay, but I'm actually holding a real battery with me. Okay, maybe I mean real DAC hardware with me. Okay, which is generating real voltage and measuring the real voltage as well. So
Now for battery management system, if I have to emulate, okay, okay, I can see it. Yes.
yeah.
For battery management system, sir, if this output we have to connect directly to the hardware, this DAC will be connected and DAC output will be connected to the LabVIEW.
Yeah, there are many ways to achieve this. Yes.
Okay, so directly it will measure the instantaneous real values.
Yeah, exactly. That's the actual idea. Either two ways you can go. Either you can build your own battery management system algorithms in LabVIEW, okay, and make LabVIEW process the data. Or battery management system, you can make it as an embedded system. Most of the time, battery management system should be independent from the computer, and a battery management system will be a hardware which will be running the algorithm. Okay, and inside that the embedded system will have a processor, and that processor will be having some ADC and DAC, okay, which will be making the measurements, and this processor itself will be processing. Okay, and this embedded system you can do it using embedded C or anything, but NI itself has some hardware, like yesterday we were talking about compact Rio, okay, which is having both um, you know um, you can say it has its own ARM processor inside it. And in order to program that ARM processor, you don't need to go for another programming language, okay, because Labview itself can be used to program that ARM processor. Or let's say if you want to make some high-speed measurements, most of the time for battery management system, we don't need to make high-speed measurements. Okay, but let's say if you want to do it, okay, you can also go for FPGA-based units. Okay, because compact Rio already comes with FPGA inside it. Okay, you can make measurements and you can also run heavy duty algorithms related to BMS in that embedded system itself. Make measurements, compute, data which is necessary for a battery management system. Okay, and then display this data in a fruitful manner as well. So this can be done by using Labview based units. Yeah.
Sir, where this FPGA role will come into picture? I mean, before battery for the training purpose or for the controller training purpose?
Most of the time for controller. Okay, for both controllers, sometimes for algorithm running as well. Okay, to compute the data. Okay, maybe for SOC calculation. Okay,
For SOC calculation, FPGA can be
it can be
used.
used. Yeah, because
Um,
there are different types of SOC calculations are available nowadays. Okay, maybe you'll be going for direct measurements. Okay, the direct measurement need not to go for any complex calculation. Okay, but let's say if you want to go for, let's say, an adaptive methods. Okay,
Hmm.
where the complexity of the formula will be very large, and the amount of computing requirements will be high. So in that case, FPGA will be much faster compared to a processor. So in that case, we may go for an FPGA.
Okay, sir. Sir, that BMS modules in that three types you have shown, centralized, modular,
Yeah, yeah,
and
yeah, yeah,
distributed.
yeah.
Now, for this distributed, you have said that each and every cell will have their own microcontroller.
Yes, yes, yes.
So that is for distributed means we cannot make that battery cells in parallel or series and like that way.
No,
Why
we
we
can.
need for the for each cell one microcontroller?
Each
Simple.
cell will, will be, measuring the, the voltage across it, and how much current it's discharging also will be monitored by that own microcontroller itself. So by using some algorithms, we'll be able to know how much, voltage is available in this whole unit, or how much current is being, discharged from this unit. So that configuration can be done. Yes.
Okay, and for the protection purpose, you have shown some protections also, over voltage, over current, under voltage, and that temperature and pressure measurement like that.
Yeah. Yeah.
So there's a which means if I want to do for the instead of using lithium ion or these batteries, if, use the sodium ion batteries. So this system will work for that also, sir.
No, no. If the battery type changes, then it's not a universal, solution for all the things. Of course, okay. Most
Mm-hmm.
of the time, we have worked on, lithium-based techniques only. But if you're going to go for something, okay, depending on the requirements again, it will change. Okay, the
Okay.
problems with respect to that will change, of course.
Okay, okay, sir. Thank you, sir. Thank you.
Yeah. So yeah, thank you very much for the question, ma'am. So if anyone else has any questions, if not, then just drop the question onto the, comment section. I will be happy to answer it. So now coming back to the, let's say you're going to develop some, algorithm, okay, or basically to bring the data of the battery to your development environment so that you can process the data. Okay, again, there are different types of, BMS components available. Either you can develop your own BMS, okay, by collecting the required data from the battery. Okay, and most of the time that's what is required for many of our clients. Okay, or there are ready-made solutions provided by some OEM. Okay, some ICs, battery management ICs, okay, which already has these measurement capabilities. Okay, it's going to be a package, okay, to which you need to make the connection of the battery, okay, cell. Okay, it is going to make all these calculations and just going to send you the data to you. Okay, so that is available in the bulk, component. Okay, it's going to be available. So our objective is just to uh, use a controller to just fetch data from that hardware. Okay, but let's say you want to create your own BMS. Okay, in that case we need to go for a data auction system which can make measurements of the battery. Okay, right now I'm just using a very simple hardware. Okay, but most of the time to create, first to prototype the BMS, okay, we'll be using a specialized hardware, okay, which can make measurements up to 1,000 volts. Okay, we should have a DMM which can make a measure up to 1,000, 1,500, or 2,000 volts DC. Okay, something like that. So let's say right now we have seen that your computer can directly connect to, to your measurement system. Okay, how to, if let's say you want to create your own software, okay, own program which can not only make measurements but also further take away to, let's say, to compute required information. So in that case we'll come to Labview. So we already know from yesterday that Labview is a software which is graphic in nature, which does not have any complex syntaxes. Okay, we have seen that a lot of things are available inside the Labview. Okay, apart from that, your Labview, okay, can also easily integrate with hardware. Okay, and that is done by using several, drivers. Okay, like yesterday, I mean, like a few minutes ago, I've shown that there's something called oscilloscope, which I'll show. So this oscilloscope, even though it's available as a ready-made application for me, it was actually created by using LabVIEW. These knobs, okay, these components, okay, these are created by using LabVIEW. And to be observant, okay, so these knobs or everything is available in LabVIEW as well. Okay, we see this dial. Okay, this was created in LabVIEW. Okay, this drop down list on whatever it's acquired here. Okay, it's going to be available as one component, right? So it's going to be available here, one form or another, right? So this is a GUI, okay, which was created by someone, okay, who wants to use an oscilloscope. But rest assured, you can create your own application which will look like in your own advantageous version, okay, and that is going to be used by you, right? So yeah, in that case, mostly for BMS, there is no ready-made application available. We need to create an application, okay, which will be used by someone else. So your BMS should be capable of measuring, voltage and current, okay, from the battery and load circuit. Okay, so for that, right now we've seen that your hardware is capable of making measurements in the battery. Okay, we are yet to see that your LabVIEW unit has software toolkits which are capable of processing the BMS as well. But how to make that measurement is what we are going to see now using this software. Okay, if you see LabVIEW, okay, it has drivers which will integrate with hardware with ease. Okay, so if you see, I'm using some hardware called as DAC hardware. Okay, and this DAC hardware, in order to interact with the Labview software, we have something called NI DACMX, which is nothing but the driver. So using this driver, we will communicate with the computer, communicate with the hardware. Okay, whatever command we send, okay, so whatever block we keep, it will be sent as a command to your hardware. And of course, this is a bit, you can say it's a bit advanced for simple users like us. Okay, so this should not be a roadblock for people who are already familiar with BMS algorithms. Okay, but we need to use LabVIEW to make the measurements. So there are many people like that, okay, who are in R&D. Okay, they don't want to learn the inbuilt mechanisms of how LabVIEW works. Okay, but they just need to make measurements of the battery. Okay, then get the data into the programming environment. Then after that, it's up to them. Okay, they can use the data acquired, then apply it to algorithm developed by them. Okay, then get the instantaneous results. So they don't need to learn in depth about the LabVIEW program. So in order to make such thing, okay, NI has introduced this simple to use functions, okay, which will be having this blue color background, something called DAC assistant here in this case. Okay, so this is specifically used for DAC functions. And here, no specific programming knowledge on LabVIEW is required. You just drag and drop that function. And what it's going to use basically is going to do is it's going to ask us some simple questions. Okay, it's going to ask us what type of measurements tasks which we need to do. Either we need to make a measurement of basically maybe a voltage measurement, or we need to generate some voltage values. Okay, or maybe we need to generate some digital data, or maybe control some digital unit, maybe a production unit. Okay, maybe your voltage level has gone up. Okay, maybe we need to switch on, we need to activate the relay. So depending on that, we can generate or acquire signals. So let's say I need to acquire voltage from a battery. Okay, I have this you know, options, okay, whether analog or digital or counter, whatever it is. So maybe I need to acquire some analog data, okay, that is a voltage data from battery. So that will be basically analog. So you can acquire voltage value. Okay, depending on the hardware used, you can measure voltage, current, resistance, frequency, okay, acceleration. Okay, of course, this hardware is a simple device. Okay, it cannot measure everything. Okay, but what indeed you can measure is it can measure voltage. So I'll tell that, and it'll show me the appropriate, channels which can make this measurement. So it's showing me, AIO0, AI1. Okay, I also have some audio input which I'm not going to use, inputs which I'm not going to use. And you also have a DMM. Okay, if you want to make high power measure, high voltage measurements. Okay, so even though I say high voltage measurements, this DMM is not really used to measure 300 volt RMS and all. Like normal DMM will be used to measure. Okay, this can measure up to 60 volts. Okay, that's it. Right, so if you want to go high above that, then you have to go for appropriate hardware specifically used for that purpose. So I'll go for A0. And I'll be having this setup. Okay, so here if I want to change anything, I can change. Okay, but I'm not going to change anything. Okay, depending on the specifications of the card I'm going to use, okay, I can control how much of voltage I can measure. Of course, you have to specify the rate. Okay, you have to consult the data sheet of the hardware. Okay, in order to check how much of the voltage it can measure. Okay, so this particular hardware, it can measure only plus or minus 10 volts. Okay, so if you want to go more about that, you have two options. Either you have to use a signal conditioning circuit to down convert, attenuate the signal to equivalent value of the same. Okay, or you need to go for another other hardware specifically used to measure high voltages. Okay, so if you are good at designing an signal conditioning circuit, okay, if you have something which can down convert the thousands of voltages from the battery, okay, to a range of 0 to 5 volts. Okay, so the 0 to 1000 volts should be down converted to 0 to 5 volts. Okay, if you know how to do that safely, we can do that. So once that is done, okay, you can just click OK, and we don't need to write any program for this. This particular block will create a program for us, not to access the hardware. Right? So this will be here. So now, if I just create indicator out of it, I can right click on the terminal. Okay, like lab yesterday we saw. Okay, we can just right click and create a numeric indicator to see how much voltage it is. So if there is a signal conditioning, okay, it will give us equivalent voltage across that signal conditioning. Okay, we need to create a calibration formula here to convert it to an actual value. Okay, maybe it will be linear fit. Okay, anything. Okay, so it depends. So now if I just run this, it will just give me, every time I run it, it's going to give me random value because I have not connected anything over there. So it's going to have some noise over there. Okay, it's not going to be perfect, and depending on the noise, okay, it's going to be like how much resolution of noise we can trust or not trust. So right now we are just going to make measurements one by clicking every time we click. Okay, it's going to be making the measurement. But of course, if you know how to use Labview effectively, you can make use of some programming constructs. and you can make the measurement continuous. And you can also include a stop button to stop measuring as well. And you can also add some sort of delay. Okay, instead of making measurements as fast as possible, you can make the measurements timed. Okay, like every 250 milliseconds or something. So it's totally up to us. So right now I don't have any batteries with me. Okay, so let's say I want to simulate some battery. Okay, even as you can see, you can also emulate a battery as well. Okay, so for a battery emulator, you just need to have a hardware which can generate voltage. Okay, so if you know how to create a model of the battery, okay, you can probably do that, and you can use a hardware to give the same output that the battery will give. So what I'm going to do is I'm going to create another parallel loop. Okay, and I'm going to generate voltage out of analog output. Basically, it's going to just generate. So I'm going to go to measurement IO, DAC assist, acquire. I need to generate analog output voltage. The reason why I'm setting AO0 is because I have already made the connection as you saw my video. Okay, so I've connected analog input to analog output, analog input 0 to analog output 0. So whatever I generated in analog output 0 will be reflected in analog input 0. And of course, this hardware is typically like it can act like an oscilloscope or it can act like a power supply. Okay, when I say act, okay, it's not going to work as a power supply or oscilloscope. Okay, but it has certain features of it. Okay, a real oscilloscope will have a much larger bandwidth than this hardware. Okay, but it has some features. Okay, so and also power supply, it can source more current. Okay, until then this particular hardware cannot source that much current. Okay, but still can generate the voltage which we require. So I'm going to go for sample on demand. And I can use a knob to control the voltage. So here I can add a knob to control the voltage, which is going to go outside. And here I'm going to measure that same voltage. So I run this, and I can see here I can change the measurement. So here I'm generating and passing it here. Okay, and this value is getting generated here, and we are measuring it there. So right now I don't have an actual battery, so that's why I'm just simulating an effect of a battery, that is battery can generate voltage. So I'm just generating it here and just measuring it back. But in real world, this will be connected to the anode and cathode of the battery. Okay, and we can make the measurement. Okay, so something like that has been already done by us. Okay, so like for example here, we have made a battery discharge curve test. Okay, where we continuously keep on measuring both voltage and current to a battery which is connected to a load. Okay, and we are trying to see how it is going to keep profiling. Okay, so this was done over a period of I think it's like 5 to 6:35. Okay, like one and a half hours. Okay, or something like that. Okay, 1 hour exactly. Right. And it was no, it's not like we have used DAC there. Okay, this small hardware. Okay, we have used a specialized instrumentation based computer called as PXI. Okay, which made use of certain specific instruments specifically used for battery charging and discharging testing. Okay, something called a source measurement unit. Okay, so we are connected to that. And to make measurements, we also had a DMM as well. Okay, which we are not used as of now. Okay, and that particular battery also had a CAN, a communication protocol. Okay, which we need to make measurement, check whether it is an internal component of the battery was able to make the measurement properly. Basically, we need to compare what we are measuring is equivalent to what is being measured inside the battery. Okay, so whether that is syncing out or not. Okay, that test is being done. Okay, so this is for making the measurements. But how about processing? Okay, so right now we are just able to make measurements of voltage, current, and temperature. Okay, if you were able to make a measurement of voltage, then it's a matter of time where we can find a way to convert that voltage to current and do it off. Okay, even most of the temperature sensors are either going to give in terms of voltage or current. Okay, so and we have the provisions to make measurements as well. But next is how we can process this data. Okay, how we can get some meaningful data out of it. So that again depends on algorithm development, number one, or if we don't have an appropriate algorithm, okay, then we need to make use, so we need to check whether NI is providing certain algorithms for us. Okay, so after the measurements have been taken from your battery, what to make out of it? Okay, so in order to check that, most of the tools offer certain toolkits to get an appropriate insight out of data. So before we go into that, let me check if anyone has any questions. Okay, as always, if you have any questions, you can drop it into the comment section. I will check it out. But now, to check whether the Labview has an appropriate driver, yes, it does. Okay, I mean appropriate toolkits. Okay, just like any other programming tool like MATLAB or even Python, I believe. Okay, Python also has. I mean they have brought a tremendous amount of work in BMS based toolkits. Okay, although I haven't personally worked in those toolkits. Okay, I heard that they have some toolkits available. Okay, similarly, I mean those are not maintained actively. Okay, but an industry standard. Okay, as per the industry standard, if you see, Labview has certain toolkit called as electrical power toolkit, which is not only used for electrical vehicles, okay, but also for generic power measurements. Okay, it's like smart grid implementation of smart grid, or electric motor measurements, synchro phaser, power quality analysis, implementation of power system protection. Okay, so those kind of things are also being done by using this toolkit. Okay, and until recently they have also added support, since electrical vehicle has boomed. Okay, test systems for all that also have come up, which means we need to have provisions to enable testing of that as well. So EV power test toolkit is added. Okay, in that battery based components also included, or we also have three-phase measurements for inverter testing as well. Okay, so right now we are focused on battery, so we'll just go ahead with battery. Right, but now our question will be, now we don't have an actual battery, we don't have an actual load. Okay, we don't have an actual EV at all, electrical vehicle at all. So how can I test? How can I get meaningful information from an EV based BMS. How can I process it? Okay, this BMS is sending me data of voltage, current, and temperature, or let's say voltage and current. How can I process the data to get some data? To answer the question, yes, we don't have them granted, but of course, we have done some tests before and we have collected data. Okay, data collected over a period of time, okay, from profiling tests of EV. So we have it with us. So how do we have it recorded? Okay, basically, since if you see, Labview is specifically used not only for data acquisition and programming. Okay, another important feature of Labview, as we have spoken before, is Labview has features of data logging. Okay, so basically file IO. Okay, it makes the file IO much easier. Okay, because drag and drop methodology is involved. Okay, it's going to make it simpler. And file IO is here. Using this file IO, you just push the data from the data acquired from your hardware directly into this file, and without much need to know about what type of file it is, how to access the file functions, nothing. Just connect it, just like how would you connect a battery to a LED. Okay, so it's going to work the same way, right? So we have these profiles, okay, like logged data with us. Okay, predominantly we have EV drive profiles, okay, of battery values, from EV drive profile, EV peak power performance, and also from a hybrid vehicle, just to compare how the fully electrical vehicle performs with respect to a hybrid electrical vehicle. So our first objective is to know how to bring this data inside Labview. As I already told you, okay, so Labview has capabilities of working with files seamlessly. So the type of file which we log data using for any type of Labview based application is something called TDMS. Okay, it's basically used to stream huge amount of data into something manageable. So it's easy for us to retrieve the data as well as collect the data whenever we need. And how we do that? So of course, as I told, Labview already has certain tools, okay, which enables us to work with files. So just like how we have functions to deal with hardware, just like how we have functions to create GUIs, and how we have simple functions like addition, subtraction, we have dedicated functions to deal with files. And TDMS is no exception. Okay, it's a program which is used for scalable access of access of scalable files. Okay, this is of very large size, TDMS stream. And if you see, these functions are what we use. And unfortunately, there is no easy function, okay, like single value function to bring data from the file inside the Labview function program. So we need to do it manually. Right. So again, it's not like very hard. Whenever you want to access your TDMS hardware, we are going to first one is open that file by programmatically, then read the contents of the file programmatically, then close the file programmatically. So when you open the file, essentially what happens is the contents of the file, no matter how small or large it is, it will be brought from your HDD, okay, your hard disk to your RAM, because Labview runs in RAM. Okay, any development, any programming language will run in random access memory because your processor needs to access the data quite frequently. Okay, your SSD or HDD is lower than the RAM. Okay, so it will be brought back into the volatile memory. And what we will give here is the file path, which is available in the HDD or and hard disk. Okay, so that we will give it as a file path, which will be given as input to this function. So we can browse. Okay, I can go for desktop. I have this log data here as a theoretical drive. And if you see here, I have other options like what kind of operation do I need to do? Whether here the data is being fetched from the existing file, or maybe I can also run some tests and log the data inside the file as well. Okay, so when we did the test, we use certain functions to log the data inside these functions, so that right now I'm opening and showing it to you. Okay, but now we need to retrieve the data back from the original test. Okay, so that is done. So once that is open, I'm going to get something called as a reference. Okay, that is the memory location in my random access memory. That needs to be given to the next function, like this. So sometimes your Labview programs will produce some errors. Okay, like any other programming language will produce errors. So in order to communicate that error to next function, we'll be using something called error wires. Not only will be communicating the data to the next function, we'll be communicating error information and other things, okay, through the single wire. So once that is done, okay, so once this function is like basically read data. So we are saying opening the file, we are reading the contents of the file. Then after reading the contents, okay, we no longer need that file onto the your hard disk, so we can close it off without further ado. And here what we'll have is we'll have the data. So I can just create an indicator by right clicking and creating indicator, and this is what will be inside your file. Okay, the file data typically will be an ASCII data, but your Labview will make the provision as to convert the data to something which your analysis files can use it. Quite simple. So when I run this, you can see the data is being fetched. Data has been fetched. You will have two channels of waveform data. Okay, one is actually voltage data, and the other one is actually current data. Right now, if you see the data like this, okay, it doesn't really make any sense. Okay, because we human beings are visual beings. Okay, it's better if you see the data visually. So instead of using this, what I can potentially do is I have some visualization objects in Labview called as waveform graph. And it makes absolutely good sense for us to use it. Again, I run this, and this is the drive profile. Okay, so during the switch on time alone, the interest current will be so high. Okay, but once everything is switched on, okay, during the drive time, okay, it's not going to be that much of the, consumption of current. Okay, but this is how it's going to be. Right. So again, this data is not going to make any sense for us. Okay, we have to calculate certain values like maybe energy brought down from the battery, or let's say you can say not only energy, we also need to have charge. Okay, so these values should be calculated from the available voltage and current. So how do you proceed in that case? So turns out that we have certain functions. If you see in electrical power simulation, okay, EV test, we have certain functions like integrate watt to joule. Okay, joule is nothing but the power, energy of the battery, energy expended by the battery. And in order to get the coulomb, that is but nothing but charge, okay, we'll integrate it to ampere. So we need to extract these values to get the data. So basically, I have both voltage and current data. What I can do is, this is basically an array of waveform information. I need voltage and current separately, so I'll use a indexing function to basically separate voltage and current. This will be voltage and this will be current. And I want them as a single value, okay, voltage and current value separately. So I'll extract only the amplitude information alone. So this is a waveform information. From the waveform information, I'll fetch only the amplitude for a period of time. Okay, so it will be a multiple array of kind of thing which will be available here. So now I have voltage and current, both of them. Okay. And to calculate power, okay, because here they say, okay, it's like integrate watt to joule, meaning its power will be integrated to joule. So in that case, we need to have voltage and current product. This is a single point value. Okay, so we can basically multiply. Okay, it's a waveform multiplication, meaning there will be no changes. Okay, I can basically multiply voltage and current, which will give me power. Every instant of voltage and current will be multiplied. So there will be nothing like losses over there.
ಇಲ್ಲ ಹಾಗೆ
Yes, I thought I had some.
No, Rajkumar, that was accidental, I guess.
Oh, okay, fine. So yeah, in that case, here if you see, we have voltage, current, and power right now. Okay, now we need to calculate your joule value and ampere value. Okay, so since it's like with respect to time, I need to send values one by one. Okay, so it will be integrating for every iteration. Okay, so typically it makes sense for us to use a for loop, and that's what we are going to do. So I'll use a for loop. Okay, and I'll send voltage one by one. I mean power one by one. And one by one means with respect to time. Okay, so this whatever value you have here is an array. Inside what comes is one individual data at one time. Like let's say every 1 second, if you're acquiring this data, okay, it will be collected that value. Okay, so we use this to convert this watt to joule. Okay. So if you want to integrate watt to joule, we need the value of the watt. This is watt. And also at what interval did we convert, did we get that watt? Okay, interval. Okay, so an interval is basically, if you create, right click on this wire, it takes some time for it to respond. Indicator. Okay, you're going to see this is the interval. Right now it's showing me the default value of 1, but basically I need to use some programmatic way to fetch the data. It will be 0.2 because that's the frequency, that's the sampling rate at which we are got the data. Okay, so I just go one level below. Okay, I'm going to fetch dt, and that's what is the value of the interval. So every 0.2 seconds I acquire the data. So this is the time period, and this is the value of the watt at that instance. Okay, so we use this function to integrate it. so that the integration will happen. And possibly this first iteration alone should be reset. So this basically is iteration terminal. Okay, so for loop it's going to start with 0. Okay, so what I'll do is I'll check whether it's equal to 0. Okay, if it is equal to 0, first iteration alone should be reset, and the upcoming stuff, okay, is going to be not reset. This data I'll collect over a period of time. Okay, individual data will be collected, and at the end of this full iteration running, okay, it's going to be seen like that. And now we need, this is for joule. Okay, so we got the joule. Next is going to be your current. For current, we need to give waveform of current. So this also requires reset. Okay, and the current waveform should be given, and this is the current waveform. And the current waveform should not be given directly, obviously. Okay, so we should be separating them one by one. Okay, so we should be giving the one block of the current. That's it. Okay, so we have some function called as a waveform subset. Okay, where we can say by relative time just fetch how much of stuff which you need to get. So every 0.2 seconds I'm going to fetch, so I'm just going to give 0.2 here. Okay, and that waveform out will be given. Okay. Okay, not this one. Duration. Right. And it's asking me for integration method. Okay, it doesn't matter, but a simple tool also we can use, not a problem. And what we get here is cumulative charge. And we tend to plot all of them together. Okay, so what I'll do below is, not to make a simple comparison. Okay, I'll have voltage here, current here, power as third element, fourth one will be the charge, and fifth one will be the energy. And here we'll be having 1, 2, 3, 4, 5. Because Labview is also prevalent on GUI implementation, okay, we can adjust it however you want. Okay, fully customize the GUI as per your needs. Okay, we can say first one is voltage, current, etc., etc. And we can plot each of these values in a separate, graph as well. Okay, there was a way to do that. Okay, let's run it one time so we'll know that. So right now, everything has come into same level. Okay, previously there was a way where we can have everything as a separate stuff. But anyway, we'll be able to see these values. Okay, so here we see, the first color is, voltage. Okay, here voltage looks like a straight line because scales are same for everything. Okay, and it gets the maximum scale which we have here is 2,50,000. Okay, so that's why we had an option here, and I'm using a different version of Labview, so they have changed something. Fit control to plane. Or you can use different, you know graph for different objects. Okay, but that's going to take a lot of space. Okay, but if you want different scales for different objects, that will be the best way to go. Okay, so this is number one, voltage, current, so on and so forth. Okay, and this is for a normal EV drive profile. Okay, where we had calculated voltage. This plot number 3 is basically the um, energy. Okay, you can also additionally you can also disable what you don't want. Let's say voltage and current. If you don't want, you can disable them. Okay, let's say you want power, only power. Okay, you can enable only that one. Okay, this is the power. So basically, voltage and current is power is compound, no, multiplication of both voltage and power, current. Okay, the next one is going to be energy, I believe, charge. So charge it shows as 0. Maybe 0.2 should be given here. Okay, this is 0.2, and this I believe should be 1. Okay, so it should discharge, but I'm not sure what happened. Fine. So that will be, connected. And for different vehicles, okay, different types of plot will be. Okay, for example, and this is for, energy. You can auto scale it. Okay, so it's going to automatically adjust. Okay, this is peak power. Okay, for peak power, you can see the scale of it. Okay, energy exposed will be high at this location. So that's about it. Okay, so this have been already been created. Okay, so basically you can um, display the values in a separate stuff like this, and you can also make it look like it's acquired in real time. Right now I don't have any hardware, but you can, if you see, it's like actual, stuff has been collected. Okay, it's like collecting the data in real time. And after the data is collected, you can see all the data at once in the second, version of the unit. So you have voltage, current, okay, and charge, power, energy. You can even change the drive profile to maybe a hybrid vehicle. And this is like a record and play button. Okay, right now the measurement has been made in the same speed. Okay, and here also we are replaying in the same speed. So yeah. So if you have any questions, please do let me know. Okay, or else we can conclude the session.
Yes, participants, you can ask queries to Rajkumar now. I hope there are no queries from participants side, Rajkumar.
So in that case,
Sir,
yeah, yeah, yes, ma'am.
sir, this software is means basically if we want to do some simulations, which will
Yes.
be for different values, different using different batteries, different controllers, or this. So can it be support?
Yeah, sure. Like most of the battery BMS systems, okay, it will have a protocol in it. Okay, if it's automotive based battery BMS system, okay, it's going to have a CAN protocol. So we need to be able to, you know, get that um, data, with respect to that controller. So it's going to come to us. Okay, if not, then potentially we need to make use of, um, you know, um, measure the data directly from a battery and just implement your own BMS. But most of the time, BMS is a fixed package. So, and it's going to have a protocol. Either it's going to have a CAN if it's an automotive based system, or if it's not an automotive based system, it's going to either have SPI or some other generic embedded system based protocol. So it should support.
Also, sir, in now all the electrical vehicles contain cyber security and all these things. So, for that purpose, any electrical equipment or something used, can we simulate that in LabView?
Yeah, if we know what is the logic behind it, what is the working behind it, then yeah, sure, we can simulate and emulate it. And that's what we call it as HIL. Okay, so hardware and loop. So we can implement the logic behind that, controller, whatever the particular application is doing. Okay, and we can give the input, whatever you're supposed to give to that particular hardware to this software. So the same expected outcome can be emulated over here. Okay, so that is possible totally.
Okay, sir, one more means I don't know it is appropriate question or not. Why you are taking the power in joules, sir? Because I saw that you are taking voltage current and then power in joules. What is why it is necessary to take
No, no, no,
power
not
in
power,
joules?
it's energy. Sorry.
It's a energy in joules. Sorry, energy in joules. Sorry. Why you are taking? Because now for the battery management or everything or batteries, we are thinking in ampere hours, sir. So what is the purpose to consider in joules?
Um, I mean, in the industry, there's no specific explanation, but whatever data we log, okay, if they are expecting us in a particular, unit, okay, we just mention it as it is. Okay, so there's no specific reason. If you want to change the unit, yeah, you can do it surely, not a problem.
Okay, because I don't know, means joules. First time I saw that energy is
Yeah,
needed
ampere
in
hour is the appropriate, electrically stuff, but This particular, if you even if you see in this particular, where is it? Okay, here also they are mentioned as joule only. Okay, but generally we say ampere hour. Okay, when we talk about energy. Okay, but this particular client, they have mentioned us to take in terms of joule. Okay, so yeah, that happened.
Okay, sir. Okay. Thank you, sir. Thank you very much.
Yeah, sure. So if no more doubts, then I think I will just
Yeah, Raj Kumar.
yeah, sure.
Actually, I just wish to ask you one thing. In our institute, we have purchased this Myrio of National Instruments. You know that
Yeah,
package.
sure. Actually, I had, since the constraint of time, I couldn't spend time in it. But yeah, my area. Yes, sir. What is your question?
No, my colleague. Much we have only done some sample experiments and all with that. We
Okay.
have purchased it around 3 or 4 years back, but we didn't utilize it properly so far. So we are planning to, just like after having an interactive session with you, I just feel like you will be able to help out in making projects using that.
Yeah, sure, sir. Actually, to be honest, I was, since due to constraint of time. Okay, you can see here that I was supposed to explain academic research using Myrio for implementing a BMS. So that was I was supposed to explain, but since time was up,
Okay, fine. So
we can surely do that, sir. Yeah.
to implement I wish to implement this battery management system that is for enhancing my knowledge. Moreover,
Yeah,
I
sure.
also started having a feeling like after seeing your sessions and all, I also I put a second thought. Okay, next time I also will go as a speaker in some colleges like this because we are having this Myrio device and all.
Yeah. Sure.
So I just want to get some information from you so that I can develop a battery management system using this Labview and Myrio.
Yeah, sure.
Okay, so I will be for the next few months, I will be distracting you for gaining some more knowledge from you.
Yes, sir, sure. It will be my pleasure. Thank you.
Yeah, and now I request some of the participants to give a feedback. Varalakshmi ma'am, because many people had already given a feedback in the chat session, you might be able to see it there, Rajkumar. Varalakshmi ma'am, are you there? Lakshmi Nair ma'am. Lakshmi ma'am.
Hello.
Ma'am, can you please give a feedback
Yeah,
for
sure.
Rajkumar?
Yes, sure. Hello, sir. It was really wonderful to have a more
Hello.
hands-on session of simulation. So I'm happy that it is included in the FTP and you did 100% justice to that. Thank you very much for this, sir. I
Yeah,
hope all the attendees who have been attending this will be benefited from your talk. Really, thank you. Nice presentation.
thank you very much for the feedback, ma'am. It was a pleasure for me. Yeah.
Lakshmi ma'am, are you there? Lakshmi ma'am?
Yes, I only talked.
Okay, no, not you. Lakshmi Goswami, because she was about to say something. Okay, fine. Okay, Rajkumar.
Yeah,
So
in that case, yeah.
we will meet you soon again for the advanced level of this same FDP, for which we have applied, and we are about to get sanction for it on coming December.
Oh, that's good to hear.
So, just like how the participants are totally satisfied with your presentation, as a coordinator, I am also very much satisfied. So, I am eagerly waiting for your next presentations in our next FDPs also.
Okay, thank you very much, sir. Thank you very much for the feedback.
Thank you, Rajkumar.
Yeah.
Yeah, now I have shared the day 4 session 3 attendance. All participants are required to fill it. I just wish to convey some important information to the participants. Basically, according to this AICT ADAL FDP guidelines, 80% attendance is mandatory for you to get the certificate. And 60% marks must be scored for the assessment which is going to be conducted tomorrow. So I request all the participants, those who had missed 1 or 2 sessions in the previous days, I request all of you to be present for all the sessions tomorrow. Tomorrow we are having only 2 sessions, and for the 3rd session we will be having validatory function followed by the assessment exam. And I am getting several phone calls, emails, and queries from the participant side that to change their salutation, but it's not possible from my end, because some of the people are calling me and saying that in their name it's Mr., but actually they are having the salutation of doctor. But it's not possible to do it from my end. Whatever details you have given into the profile of AICT Adal as a participant, that is what I will be getting it. Even if I change your name salutation in that Excel sheet, it's not going to get reflected in the certificate, because the certificate is being issued from the AICT Adal website through an automated system. So whatever data you have given them, that only will be coming as printed form in your certificate. So please try to understand, and there is no further useful or there is no further meaning in calling me regularly for changing your name salutation. Please note this. And I request all the participants to be present for tomorrow. Another thing, the evaluation will be of 20 questions, and the duration of the exam will be of 30 minutes. It will be a very simple exam. The exam and all are done in accordance with the ADAL schemes and guidelines only, and it is mainly meant for issuing you the certificates, not for not issuing the certificates. So we have set the questions in a very simple manner. Even I want all the 200 participants, I don't know, only 170 to 180 are responding regularly. So even I want all the 170 or 180 participants to join tomorrow for the validatory function. Before the assessment session, I want all the participants to just turn on their camera for a moment so that we can have a screenshot of all the participants. That is also a needed thing to send to AICT Adal portal. Not now, sir. You need to turn it on only for tomorrow during the validatory function. It's not needed now. And I want all the participants to be present for tomorrow's sessions also. Thank you. So we have completed the 4th day. Thank you all the participants for your cooperation. Thank you. See you tomorrow.